Hey there, in this video we're talking about the Queue abstract data type, and this covers sections 18.4 to 18.6 in the Gaddis textbook. So in the last video for chapter 18, we were talking about the stack abstract data type, which we said is a LIFO data structure where the last thing that you put into the container is always the first thing that comes out, like a stack of dishes, or sometimes I think of like a suitcase. And we also saw the example of the call stack, that's keeping track of where the functions are coming from and going back to all the time. Incredibly important. So basically the Queue abstract data type is the reverse of that. So again, important and useful in a lot of situations. So let's look at this. Yeah, so the queue is, and this is just a standard English word. You can just look it up in the English dictionary if you need to. It's a collection of items using first in, first out access, or FIFO for short, which if you think about it is actually the reverse of the stack. Again, first in, first out, that's a phrase that also gets used in accounting, as a matter of fact. And you can also think of this as first come, first served, is what we're saying with that. So some real world examples of things that are queues. I mean, you literally call these queues people lining up for a bus or people lining up to get into a movie theater or something like that. You totally call that a queue. So whoever got there first, they're going to get on the bus first, assuming the line doesn't get broken or something like that. Whoever gets in line for the movie gets to pick the first seat. And that's what we call a queue. And that's, how those things normally we expect them to work. In computing terms, like one really good example of that is print jobs sent to a printer. Printer takes some time to print stuff out. Multiple people might be sending jobs to the network at the same time. So you have this storage area on the printer that receives the incoming jobs that are waiting for something to actually get printed, and that's totally called the print queue. And whoever sent the first job, that's actually what's getting printed right now. And whoever sent job 2, 3, 4, that's exactly the order that they're waiting to get printed in. Now, again, recurring theme here in chapter 18 is you have two different options for actually implementing one of these things, assuming you want to use them, is you can make a static queue that's fixed in size, and you're really going to be storing things in an array, okay? And of course, the second option is a dynamic queue that's variable in size, it can grow and shrink, and you're going to implement that as a linked list. There's your two standard options. You're going to see that all through these different abstract data types, and probably when you see your data structures course, again, they're going to keep ping-ponging back and forth between the advantages and the disadvantages of those two options. So, the stack, pretty simple. What you're going to see here is the queue. And in some ways, you kind of expect more things in the real world to work like a queue, first come, first serve basis. But you're going to see it's kind of weird that the queue type, in order to make that happen, has some extra complications that we didn't see for the stack. The stack in some way was simpler because you're always adding and removing from the exact same location. You're just tracking one location at the top of the stack. And when you remove stuff, you're not affecting the other stuff in the stack. With the queue, you have to track the two separate ends because stuff is happening at both ends. And when someone in a queue goes in the movie theater, everybody else shifts up. So there's these extra complications with a queue that make it a little bit more involved to actually code up. All right, so let's just talk about the locations, right? You're tracking these two separate locations. Probably inside your class, there'll be a pointer. I guess if it's a linked list version, or there'll be, integer variables for the subscripts if it's an array version. But you got to keep track of the front, which is the position where the elements are being removed from. And then there's the rear, which is the position where the elements are being added to. So there's the terminology we usually use for that. And then for adding an element to the rear, at least what the book calls it calls it NQ, putting something into the queue. And then for removing an element from the front of the queue, the implementation in the Gaddis textbook calls it dequeue, for removing a thing from a queue. Now, some implementations, I will say that the version in the standard template library uses the function names of push and pop, like we've been using for other stuff like vectors and stacks and things like that. It's kind of the customary term for adding or removing stuff from a container. But I can kind of see why why Gaddis, the author of our textbook, called them NQ and DQ, because they are working a little bit differently. All right, let's kind of hand trace this. Let's walk through an example of, I'll make a queue of characters. Again, I'm thinking of a static queue that's being implemented as an array here. It's all, actually literally next to each other. So I make a queue of characters and I call NQE, and the E shows up at the front of the queue, right? That's the first thing. And then I NQ the letter K and it shows up next. I NQ the letter G, and of course it's each new character is being added to what's currently the rear of the queue. Now I'm going to start calling some DQ operations. Which character comes out when I call the first DQ operation? And of course, it's the E. It's going to be the E. The first thing that I sent in is going to be the first thing that comes out. Out comes the E. Notice what else happened there? All the other stuff had to move forward, right? See, that's an additional complication that doesn't have to happen with stacks. But that's what you expect from people in line at a movie theater or bus. Then I call DQ again. What's going to come out now? Obviously the K, because that was at the front of the line. G moves up. Call DQ again, and out comes the G, because that's at the front of the line. So that's what's happening with a queue with NQ and DQ operations. You can intermix them, and hopefully you can kind of, predict what's going to happen with that. So there's that complication that we don't have with stacks, that stuff had to get moved forward in order to get stuff at the front of the queue for the next DQ operation. Let's talk a little bit about that. Yeah, that issue with dequeuing and possible solutions to that. So like we're saying there, when removing an element from a queue from the front, the remaining elements have to ship to the front so you've got things in the right place for the next DQ. And so that's really a copy job. So, item 2 gets copied to location 1, and item 3 to 2, and 4 to 3, and 5 to 4. And that's the thing that we didn't like when we were inspecting how vectors work, right? How dynamic arrays work, is that when you grow a vector, a dynamic array, you make a larger array and you have to copy all the data over. And that's a little bit of a wasteful operation because, again, for a large array, that's going to be a lot of copy time on the CPU that's not really doing you any good. So we don't like that about dynamic arrays like vectors. We don't like that about static queues because every time you take something out, you have to do an enormous number of copy jobs just to shift stuff up to the front. That's not good. So what could you do about that? Well, one solution would be to not always be pulling stuff out of, subscript 0, the beginning of the array, is you could bring in a new variable that tracks where the current front is. And as you pull stuff out, front goes from 0 to 1 to 2 to 3 to track what's currently technically the front without moving stuff around. Okay, that's interesting. But the problem is if you do a bunch of DQ operations, your front is going to move to the back end of the array, and then you're not going to have any room to put any more stuff. Right? At some point, the front actually hits the end of the array, and then you're out of luck because you can't actually put anything in there between the front and the end anymore. So for a limited use case, that might be okay, but obviously you're going to get stuck at some point. So, second solution would be to have a front and a rear variable, but then at some point have the rear be able to move around come in the other end of your array and wrap around like the whole thing's really circular. Okay, so the front is moving over here, and then the back end shows up over here, and then at some point the front shows up over here again. I'm getting mixed up even trying to do this with my fingers right now. So you can do that. I've seen that happen. You don't get stuck anymore. But your code starts to get pretty complicated of keeping track of, is the front before or after the end right now, and did it wrap around, and is the data wrapping around or not? And you can do that for a static queue, and I'll say that's as good as it can get for a static queue, but it gets really complicated code, and I hate looking at that, and it's really easy to have bugs, and it's really easy to screw up, so I'm not super fond of that. The book shows you a complete solution to that. So it's doable. you can dig into the first example in the book that does have a static queue, and they actually do take care of all those details. So if you'd like to see the ugliness of what it takes to do that, you can totally look in the book and see what that looks like. Now let's at least look at the interface to the book's version of a static queue class. Here they're calling it IntQueue. As usual, they're starting with a class that just stores integers. Hopefully by the end of the chapter, they'll have a template version that you can store anything in. And what's going to happen here when you create one of these queue objects, it's going to dynamically allocate a fixed size array to use for actual storage space. So among the private data, you're going to have an integer pointer called QArray that's going to be holding the address of where that dynamically allocated array is located. And of course, you have to track the size of that array as always. So here's an integer called QSize. It's holding the fixed size of that array. That number is not going to change at all. It's representing the maximum number of things that you can store in this queue. Like we said, we're going to have subscripts for where the current front and rear indices are into that storage space. And this implementation, they also added another piece of data called num items for the number of items currently being stored. Now, my instinct would be that you should be able to compute that on the fly from the difference of the front and rear indices. But I guess in their implementation, they found that kind of convenient to just have that stored there all the time. So among the constructors in the public section that the application programmers can actually use, like we said, here's a constructor that takes an integer for the starting size of that array, the fixed size of the array that's being held internally to the queue to actually store stuff. You also have a copy constructor. We said that's pretty common. If you need to, you can make a duplicate of a whole queue, and it sets up a brand new object, copies all the data over. Now you have two of those queues. Going to have a destructor here that's basically going to deallocate that array that's inside it before the object goes out of scope. And then here are the basic operations. You're going to have an enqueue function that takes a new integer value, stores that in the queue, of course. The dequeue, how they set that up, it takes an integer reference. You've got to have a variable there to receive the outgoing value. So when you dequeue something here, you have to provide a variable in which you're going to store it as it comes out of the queue. That's not the only way you can set up one of these container objects, but it makes sense to me, so I think that's a pretty good way of doing it. Then you have those testing functions. Is this queue currently empty? True, false. Is this queue currently full up? Is the array all maxed out? True, false. And a function called clear here that's just going to get rid of all the items currently in the array. And all you really have to do is just set front and rear indices back to the start, and then effectively you're able to store a bunch more stuff in the queue. That's not going to actually destroy the object like the destructor would, just clear out the stuff in the array, and now you can use it for more storage space. And let's look at an example of a demonstration of actually using this queue class. Very simple little example out of this section of the book, but hopefully we can predict what's going to happen when we see it. I've already made a project in Dev C++, and I've added this program here. Program 18.7 is what we're looking at. This makes use of the IntQueue header we just saw. This makes use of the IntQueue implementation code, of course, over in IntQueue.cpp. So I've added all that stuff together here. As I look at this stuff, here's the header, like we just saw, of course. Here's the implementation code in the CPP file. And again, I don't really want to look at all this complication, particularly the complications around the wrapping code. But if you want to, go ahead and you can see exactly how that's done. There are the constructors and destructors. Again, these lines right here in the enqueue dequeue is the extra work happening to get the front and rear wrapping around properly. There and there, you can kind of think of that on your own. Those other tester functions here, they're pretty simple. Here's the actual program that we're looking at, 18.7. Remember that there's the classes tab in Dev C++ that will remind us exactly what's in the classes that we're making use of here. There's that IntQueue class with all the public functions up top, the private stuff that we don't really care about as the application programmer down bottom. So we can just refer over to that if we have questions about it. So what does this program do? Well, it makes an IntQueue object, and they're going to call it IQ. And of course, every single one of these constructors takes a parameter. So you're calling the main constructor here that takes one integer. And in this case, you're making a queue that internally has an array size 5, so it can hold up to 5 things. And then there's this block here that's going to say we're enqueuing 5 items, and feel free to change that number when you test this out yourself. Here's a for loop that is going to try to enqueue the numbers 0, 1, 2, 3, 4. And then it's going to say, now we're attempting to enqueue again. And here they're going to enqueue the number 5. And then down the bottom here, they're basically going to retrieve all the items out of the queue. The values in the queue are setting this loop up as a while loop, very intelligent. So as long as the queue is not empty, apparently you've got some more stuff that you can take out. So as long as the queue is not empty, make that integer variable we talked about that you need to actually call the dequeue function, because it does take a reference to a variable. It's going to receive the outcoming value. Call IQ.dequeue. Put the outgoing number in value there. Print that out. You're going to see what it is. So I think that I would like to run this in the debugger. And I will compile this. Great, great. And so now, make sure I have enough space. You're going to run this in the debugger and see exactly what's going on in it. There we go. All right. So program has started up here, hasn't printed anything here, just starting on the first line, and I can go line by line. So let's see here. So creating the integer queue. I could put a watch on here and keep an eye on what the state of the integer queue is right here. So there's the address of where the dynamically allocated array is in the memory system. We could actually dig into that more if we wanted to. The queue size is 5. Currently, the way the implementation is set up, the front was set at -1 and the rear is set at -1. And obviously those aren't actually legitimate indices into an array, but they will, once things get put into them, they'll become legitimate subscripts. Currently, the number of items is 0, of course. So going into this for loop, says we're enqueuing our 5 items here. And you can see here as we go through here, we are enqueuing the number 0. So as we do that, the number of items becomes 1, and the rear of the queue, right, the last thing we stored is in subscript 0. So as we go through this, kind of keep an eye there on the number of items and where the rear currently is. Added another thing, and another thing, and another thing. Right, and there we go. So at this point, we have 5 items stored in our queue. And the very first thing is actually sitting in subscript 0. The last thing is sitting in subscript 4, which is being tracked by that rear number there. All right, so now it's going to attempt to enqueue again, and it says we're going to try to enqueue the number 5. Maybe pause the video and see if you can predict what's going to happen when line 20 runs. Hopefully that's pretty obvious because we've got the array filled up. The array inside our container only has 5 slots. We've used all of them. So when this calls enqueue with another value, whatever it is, we're going to have to get an error message. Let's see that. Yeah, so now attempting to enqueue again, and it says the queue is full, so you can't enqueue anything more. The number of items doesn't change. But you can actually see where that error message comes from in IntQueue. That's part of the queue's implementation there. And so now we're going to try to get the values back out again. So the values in the queue were, and obviously the queue is not empty, so there's going to be something we can get out. So once again, maybe we're going to go through this until the queue is actually empty. Maybe pause the video again, and if what we've said in this lecture so far makes sense, hopefully you can predict what the next couple of things that show up on the screen are. All right, and of course the whole point to a queue is that it's a first in, first out data structure. So whatever we put into the queue first, that's what we're going to see next. And the first couple of things what we put into the queue were 0, and then 1, and 2, and 3, and so forth. So let's confirm that this is working properly, get something out, and we get out the 0, right? Queue is still not empty. Going to get some more stuff, get the next thing, print that out. We just got the 1. And the next thing is going to be the 2, obviously. Right, so it looks to me like this queue is working as advertised, and we are getting the stuff out in the same order that we put them into. Now, of course, that's different from a stack, right? If we did this exact same very simple experiment with a stack, we'd get the stuff out in backwards order. So if you push into a stack 0, 1, 2, 3, 4 and start popping, of course, you're going to get 4, 3, 2, 1, 0. And you can see here that this queue actually is working, and you get all the stuff back in the same order that you got that. Now, I'll also point out as we did that, right, as the number of items went down, the rear of the queue stayed the same, but the front came forward. So you ripped something out of index 0, and then it was saying, well, the front's currently index 1. So as we said, instead of literally copying stuff forward like you do in real life, actually, we're doing this business of just move what counts as the front to avoid that copying. And this is as efficient as you can make a static queue. So this totally works. But you can probably guess what I'm going to come to next, right? Really, for queues, the much better option is to make a dynamic queue that's actually really growing and shrinking for real as you NQ stuff or DQ stuff. So like we said for a stack, you have this second option here of a dynamic queue where you've really got a linked list internally, keeping track of that stuff. And so now all kinds of advantages. Now you have dynamic sizing, right? Exactly how many things you've added. That's the size of your list. And it avoids this kind of nightmarish issue of shifting the elements and wrapping the indices. You know, you're not doing copies. You're not shifting the elements and slowing the program down. You're not wrapping the indices around and having complicated code for this. So what you will have for your linked list is you'll literally have 2 pointers, one to the front of the list, one to the rear of the list. And every time you NQ a new thing, you just append to where the rear pointer is pointing at, right? Just like the append operation with our linked list. And then anytime you DQ something, you just have to delete the very first thing. Just delete the thing that the front pointer is aimed at, and then aim the front pointer at the next thing. And so that takes away all those complications. There's no wasteful copying happening to shift stuff. There's no complicated wrapping job. There's no keeping track of the indices. You just literally have a pointer to the front and the rear, and you can add things one at a time, and you can remove things one at a time. That's kind of what you want, frankly. That's a much better solution. I like that a lot. Okay, so building them out. What are some options for building a queue? Again, you know that a queue's going to have an NQ operation. You know that it's going to have a DQ operation, or push and pop, whatever you want to call it. Depending on your usage, you might have additional functions that you also want to have added in there. And if that's the case, you can write your own queue, make it do whatever you want. Wonderful. So the book has, one version of a static queue to store integers called the IntQueue. Great. And then their second example is, really even better, a dynamic queue to store integers that they call dyne_IntQueue. And you can check in on that. And I feel it's cleaner code. Of course, it uses pointers. It uses dynamic memory allocation. It's just got a linked list inside, of course. I feel like that's cleaner, easier to read code for myself. Now, of course, those only store integers. So what you really, really want is you want a class template version of a queue that will store anything, of course. Integers, floats, chars, strings, feet, inches objects, inventory items. Of course, that's what you want. So the book has complete code to a class template version of this called dynamic queue. And it's dynamically allocates stuff, resizes perfectly, no complicated code, stores anything you like. I mean, that's great. That's what you want. So again, we don't have the time in this video to go through all the details. I'll leave that for your data structures course, but you can get a head start. Just dig into the Gaddis textbook and they have the entire details to a fully templatized dynamic queue. And you can dig into that and you have a great head start on your data structures course. But again, if you don't want to write your own code, don't forget the standard template library provided you all this stuff, right? They've got template class versions of everything we're talking about here. So you can just just use the free version in the STL for queue. Actually, there's 2 related containers like this. There's a container called queue, which is this container abstract data type that can be used to provide a queue. And again, like we said for stacks, you can choose whether it's actually storing it in a vector, which is an array, of course, or a linked list, right? You get to choose that. And it has member functions to add and remove stuff. And like I said here, the STL calls them push and pop. You push something on the end of your queue, you pop something off the front of your queue. Great. Now, in addition to that, right, they also have a slightly more advanced thing that they called a deck. Deck, which is short for a double-ended queue. Deck for short. So here, that provides you with the opportunity. I mean, you already have pointers to the front and the end. So in the deck, you can add stuff to either end. You can remove stuff from either end. So a little bit more flexibility to the application programmer, and they can do either one they want. So here you have two push functions. You have push front, you have push back, and you can add stuff to either end you want. You have two pop functions. You have pop front and pop back, and you can kind of see how that works. So, I think a lot of programmers would probably just use a deck, frankly. They just don't think about it. They just get in the habit. If you only need to add to one end and remove from the other, of course, you can use a queue. That's what we're talking about here. But, you might just get in the habit of using a deck, and you can add to one end and pop from the other. I mean, like a queue does. But then if for some reason you need to reverse that, it's built into the deck. So I think a lot of professional programmers would probably just go use a deck in the first place, get accustomed to that, and then you can do either one you want. Couple different options as usual. Let's see exactly what that would look like if you wanted to make an STL queue or deck. So you have these two separate header files, these two separate libraries. You've got the queue library, you've got the deck library where that is defined in STL. So you have to pick one and pound include it. And then, very, very simple. If I want to declare a queue to hold characters named CQ, here I'm doing that in standard class template fashion. So I'm making a queue of characters, calling it CQ. Or, not any more complicated at all to make it a deck. Here I'm declaring a deck of characters and calling that CQ. Okay, so do whichever one you want. There's some other details in the book. Again, here, I think by default, it makes it a vector. I guess I'd have to look up now. But you can add a second parameter to take control of how it's actually storing the data, and you can make it actually use either a vector or a list, depending on your choice. Here, I think it's a vector by default, I think. I could be wrong about that. I'd have to look it up. All right, so there is the end of our very brief introduction to these two abstract data types, very common in computing, stacks and queues, which is the subject of Chapter 18. And again, stacks, LIFO, last in, first out. Queues, FIFO, first in, first out. And again, we got to use stacks for the call stack in any program, and we need to use queues and things like a printer queue are good examples of that. And I'm sure you can think of more examples on your own. So I would recommend that my students, browse Chapter 18. Pick something that you're interested in, right? Are you more interested in the static version with the arrays and the complications with that for queues? Are you more interested in the dynamic versions that are using pointers and dynamic memory? Maybe look at the class template version, or maybe look at the STL version. Maybe pick one that you're interested in, and we could focus on that in the next lab. And of course, look at the review questions at the end of Chapter 18, particularly multiple choice or fill in the blank type stuff, true false stuff, because any of those things are fair game on my final exam, the way that I teach the course. And I would get together with my students for a lab maybe like this, and maybe for this lab we would dig into the dynamic integer queue and get a little practice with how that works. And as usual, read the specification, right? Get a little bit more practice reading header files and seeing what services the class is supposed to provide us. Write a test driver as usual to confirm that we can make one of those objects, we can call the public functions, we know what they're supposed to do, and we can confirm and double check with our test driver. So getting a little bit more practice with object-oriented programming and learning more about queues and getting a head start to your next classes like data structures. Again, maybe I'd give my students the choice. Maybe I'd say you want to use the static queue or the dynamic queue, right? And possibly then I would, once we do that, I would maybe swap out for the other one once we have our test driver, see what it takes to swap one out for the other. Hopefully, it doesn't take too much work, assuming all the public functions match up, I guess. And I mean, what would be really great is if you had a base class, if you had a class hierarchy with a base class. I mean, it could even be an abstract base class, and then it shouldn't take any work at all to swap out. I don't think they did that here, but that would be even better. So we'll think about that, right? Think about how easy it is to swap one for the other once you have a program using a queue. And that's all. That's a really good practice for your next class. All right, so next time, oh, I see. So next time, chapter 19 is about recursion. And wow, again, such an important topic in computing. I wish we had more time for it actually, but we're going to get a brief introduction to recursion that might possibly be really important in all your future computer science courses actually. Computer architecture is going to be talking about that with assembly language. Data structures, I'm sure we'll be talking about that maybe half the time. Maybe you'll take a discrete mathematics class where you'll be talking about recursion and induction. It might be part of all your future classes. And the basic idea of recursion is it's a really clever way of doing repetitions without loops. Is if you set your functions up properly, a function can call itself. I don't know if you've ever run into that before, but in addition to calling other functions, a function can call itself repeatedly to get some kind of job done, kind of like it's a loop. How does that even work? Well, it uses the call stack. That's what it does. It uses the call stack to stave information as it calls itself repeatedly. So incredibly powerful, incredibly important subject, recursion. So you really ought to watch that next video to get ready for your future classes. And I'll look forward to seeing you then.